Hello again. Okay, so this is part 2 of the video series Contractive Sequences are Cauchy. So in the previous video, we defined what it meant to be a contractive sequence. You're contractive if there exists some c in between 0 and 1, such that neighboring terms pn plus 2 and pn plus 1 is less than c times pn plus 1 minus p sub n for all n. And then we had this claim that the sequence is contractive if this condition holds. So going to prove now that every contractive sequence is Cauchy, and hence in complete metric spaces those sequences will converge, such as in R. So proof. Let x sub n be contractive with contractive constant c, and we know c lives in 0, 1. So that's what it means. For some fixed c in 0, 1, we have a contractive sequence. Consider x sub n minus x sub m. And wait, bad form. Let epsilon be greater than 0 be given. We want to show that there exists some capital N in the naturals such that for all n m bigger than or equal to this capital N, we have the fact that x sub n minus x sub m is less than epsilon. Okay, to that end, let's consider x sub n minus x sub n. Without loss of generality, we can suppose that n is bigger than n. So x sub n minus x sub m is equal to x sub n minus x sub n minus 1 plus x sub n minus 1. So I'm just adding 0 in a weird way there. And I'm going to do the same again. Minus x sub n minus 2 plus x sub n minus 2. So I added 0 again, etc. down to the last term, x sub n plus 1 plus x sub m plus 1 minus x sub n. So I've added a bunch of zeros in between x sub n and x sub n and x sub m. So this is called a telescoping series. And I'm going to associate the like terms, x sub n minus x sub n minus 1. I'm going to associate those two terms, plus x sub n minus 1 minus x sub n minus 2, plus dot dot dot, down to this last one, x sub m plus 1 minus x sub n. And then this is less than or equal to, by a triangle inequality, the following. X sub n minus x sub n minus 1 plus x sub n minus 1, the subscript should be fixed, minus x sub n minus 2 plus dot 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 down to this last term, x sub n plus 1 minus x sub n. Now to each of these, I'm going to impose claim star. By claim star, x sub n plus 1 minus x sub n is less than or equal to c to the n minus 1. The exponent is 1 less than this index times x sub 2 minus x sub 1. So applying that to the first one, this term itself is less than or equal to c to the power 1 less than this index, c to the power n minus 2 times x2 minus x1. This term is less than or equal to c to the power 1 less than this, n minus 3 times x sub 2 minus x sub 1. Dot, 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 down to this last one, which is less than c to the power 1 less than m, n minus 1 times x sub 2 minus x sub 1. This is equal to, I have a bunch of different exponents of c, and each term, x sub 2 minus x sub 1, is in all of these terms. So I will factor out all of the c terms. C to the n minus 2 plus c to the n minus 3 plus c dot 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 down to the last one, c to the n minus 1. All of that times x sub 2 minus x sub 1. So now I have here, remember, c is a number between 0 and 1. And here I have powers of c that are increasing. This power is 1 less than this power, which is 1 less than this power, all the way up to this power. So this is a partial geometric series right here. And my claim is that I can make this less than c to the m minus 1 over 1 minus c times x sub 2 minus x sub 1. So this is the claim. We're going to call this star star. I'm going to prove that this bottom to last line is strictly less than this bottom line. If so, then I know that as m goes to infinity, c to the m minus 1 goes to 0. So I can definitely find a capital N such that this is less than epsilon. That capital N is guaranteed because I know no matter how small epsilon is, I can find a value such that past that value m will be c to the m minus 1 converges to 0. So that whole thing can be made as small as I desire. So to that end, I think I will have to fit that in over here because I want to keep this on the board. So let's erase some of this. Okay. So the rest of this proof is kind of trivial matters from Calculus 2. We just remember some facts about geometric series. So a fact about a geometric series, we have to remember, what do I use actually here? I don't use much. Well, we use the fact that 1 plus r squared plus dot 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 plus r to the n minus 1 equals 1 minus r to the n over 1 minus r if r is an absolute value less than 1. Recall that from Calculus 2. So we're going to use that fact here. Our c is going to replace our r. So what I'm proving is that this line here is strictly less than this here. So to that end, I'm going to write this in increasing order. So we have c to the m minus 1 plus c to the m plus dot 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 plus c to the n minus 3 plus c to the n minus 2 that whole thing is equal to c to the m minus 1. If I factor out the c to the m minus 1 here, times 1 plus c plus dot dot c squared plus dot 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 plus c to the what power is left? Well, it's not too hard to see if I'm going up to n minus 2 and I'm factoring out an m minus 1 from c to the n minus 2. I have n minus 2 plus the m minus 1. That's clear. And this exponent is just n minus, sorry, this is a minus. N minus m minus 2 minus minus 1 is minus 1. So this exponent is just that. So this is really just c to the m minus 1, 1 plus c squared plus dot 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 plus c to the n minus m minus 1. Now, using the fact of a geometric series has this closed form, this is c to the n minus 1 times 1 minus c to the, this power r is 1 higher than the last term. So 1 higher than the last term would make this power n minus m, all over 1 minus c. And then I notice something. This is just c to the m times this ratio. This is less than c to the m minus 1 times 1 over m minus 1. That's clear because since 1 minus c to the n minus m is strictly less than 1. This is a clear fact. 1 equals 1, so if I subtract c to the n minus m from one side, that'll make the left side smaller. So I've just replaced the numerator of this fraction with something much larger, so the whole fraction becomes bigger. So this is clear here. And so that's basically how we prove hence star star holds. I just replaced my multiplicand here with something larger, which is this here. So what exactly is my capital N? Should I really care for that? You probably should, because I just said in words that since as m goes to infinity, c to the n minus 1 goes to 0. But what is the exact capital N that we seek here? Well, if we set, I'm getting a little particular here, but I think this is an important point. I want to make this less than epsilon. So I know that there exists a capital N such that this whole thing will be less than epsilon. But what is that capital N? Well, I'm going to choose, let's take this and solve for little m. So, finding the capital N. So c to the m minus 1 over 1 minus c times x sub 2 minus x sub 1 is less than epsilon if this happens, if and only if c to the m minus 1 is less than epsilon times 1 minus c over x sub 2 minus x sub 1. And then I take the log base c of both sides. It's less than log base c of epsilon 1 minus c over x sub 2 minus x sub 1. And this holds if and only if m minus 1 is less than the log base c of epsilon times 1 minus c over x sub 2 minus x sub 1. So, adding 1 to both sides, how's this looking? Adding 1 to both sides, I'm running out of space on the board here. Adding 1 to both sides, m is less than log base c epsilon over 1 minus c over x sub 2 minus x sub 1. So if I set n to be equal to plus 1, if I set n to be equal to the greatest integer function of log base c of epsilon over 1 minus c over absolute x sub 2 minus x sub 1 plus 1, then for all m bigger than or equal to this capital N, the claim that I erased holds. The result follows. Hence, contractive sequences are Cauchy. Cauchy. Okay, so there were some sloppy things I did in this proof. Obviously, the stuff I did here should be set off in some sort of lemma, trivial lemma, or call it claim star star. And we should choose our n in the beginning to be this value and show that this work holds to show that the final result holds. But, yep. Formal proof, of course, would be cleaned up, teched up nicely, and but this is a great result. Now we have a criterion to know that if a sequence is Cauchy. You just have to know, is it contractive? If it's contractive, then we know it's Cauchy, and in complete metric spaces, hence the sequence will converge. Okay, thank you.